Hello and welcome to this section on AWS Sagemaker. In this section, we will look at the problem statement on solving the Boston house price prediction problem using the machine learning concepts in AWS Sagemaker. Let's start with the initial steps toward training a model for this problem statement. So, we will be going through these mentioned steps, starting off with collecting the data for our use case, performing some exploratory data analysis on our dataset, pre-processing the data to train the model, and then after deploying the model, we will start the price prediction using the model, and finally the most important step is deleting the endpoint. Let's begin with the first step. So here I am importing the important libraries, which includes OS, Numpy, MatPlotlib for plotting, Pandas, and Seaborn, which is a Python data visualization library based on MatPlotlib. It provides a high-level interface for drawing attractive and informative statistical graphics. Then we have imported the Scipy scientific Python computation library with some of its essential modules. And then finally, we have the libraries for Bodo 3, the Sagemaker, and its module for the execution rule. Previously, we imported our dataset from the S3 bucket, but this time, we will use the scikit-learn library pre-stored dataset. Here you can see that I'm loading the Boston dataset from the sklearn datasets, and then we are loading the dataset to the variable name Boston. The keys function here will return the dictionary for the dataset. Now let's run this cell. So here the keys shows that the dataset will contain the data, which is our actual dataset that we usually call as the data frame and process to train the model. Then we have the target variable, the feature names, their descriptions for each feature in the dataset, and the file name. If I quickly look at the data and run this cell, so you see that we have 506 rows and 13 columns. I would like to mention here that these 13 are all the features, as the target, or you may call the answers or the price definitions, is stored in the target parameter. And that we have seen in the description, it is other than these 13. Let's describe the dataset using the description we already have for dataset. So here it shows the features that we have and the description for each one of them. For example, the first one we have is the CRIM, which is for per capita crime rate by town. Then we have ZN, which is for the proportion of residential land zoned for lots over 2500 square meter. And then so on, we had the description for all the feature columns. If you want, you can also download the dataset from the link here, which is for the UCI machine learning repository. I will provide the Jupyter notebook in the resource section, so you can visit this link on your own. In the next cell, here I'm printing the feature names for Boston house price dataset. And here are all the names. Now let's convert our dataset to the data frame, which is one of the essential parts for data processing. So here I will use the data frame variable as Boston_df and load the Boston.data values. Let's print the data frame head. So here we have our dataset and this is what it looks like. But you notice here that we cannot see the column names over here. So for that, in the next cell, I am adding the column names, which we saw previously here as feature_names to this data frame. Now let's run this cell and see the result. So you can see that we have the column labels also available this time. One important thing is the missing price column in the dataset. As we discussed above, it is in the target variable for the dataset. Now let's add it to the same data frame. In this cell, I'm naming it as price, and adding the target value to it. Let's now see the output and run this cell. And here we have the price column in the final data frame that we will be using. So now let's see the final shape of the data. So now we have 14 columns and 506 rows. So this is our final data frame that we have combined out of the loaded dataset from the scikit-learn library. In our next lab session, we will start with the exploratory data analysis on this dataset. In this lesson, we will perform the exploratory data analysis on our data frame which we created in the previous lab session. As usual, we will first look at the statistical analysis of the dataset. For that, we use the .describe function. Let's run this cell. So here we have all the statistics for the different features of the dataset. Like the RM, which is the average number of rooms per dwelling, has a mean value of 6.28 and it has a maximum value of 8.78. Now let's have a look at the correlation between the features. Let's run this cell. And in the next cell, we will look at its heat map. The heat map tells us the correlation relationship among different features of the data. The positive values represent a positive correlation between the two features, and on the other hand, the negative values represents a negative correlation between the same. We will be looking at the different features to know which features have better correlation with the dependent variable, that is the predicted output price. Now let's have some visual look at the same heat map. From these graphs, it can be observed that RM, tax, PT ratio and LSTAT shows some good correlation with price. So out of the 13 features, we will focus on these 4 features only. Now I will create a new data frame with variable name Boston_df1, and in here we will only store the columns we are interested in. So I have the RM, which is the average number of rooms per dwelling, the tax, which is the full value property tax rate per $10,000, then the PT ratio, which is the pupil to teacher ratio, and then the LSTAT, which is the percentage lower status of the population. Let's run this cell. And here we have the price target value with the 4 features we are more interested in. Let's now have a look at the correlation for only these 4 features. And in the next cell, let's plot the heat map for the same. Now here this cell will print the values directly that you see in the heat map. Let's have a pair plot grid view for these correlations. We can see some linear relationships from the pair plots. So from the pair plots, we observe that RM, LSTAT and price are normally distributed. Then we see that RM and LSTAT, this is LSTAT and the RM, shows a good linear relationship with the price. Some outliers can be observed in tax and price here that needs to be eliminated. Now let's have a look at the statistics in relation to these 4 features that we have selected. Here it is. Now let's begin with the understanding of these selected feature correlation. So we will first look at the relationship between the number of rooms and price. Let's run this cell. It can be observed that price is directly proportional to the number of rooms. That is, the number of rooms increases with the increase in price. And for the decreased price, the number of rooms decreases. Next, we will look for the relationship between the LSTAT, which is the percentage lower status of the population, and price. Here we can see a negative correlation, where when the price decreases, the lower status increases and vice versa. Also, let me quickly go through the other 2 features correlation. Here we have the tax and price relationship. we see a direct correlation between the tax and price. So the more the price of the house, the more the tax for that. Finally, we have the PT ratio and the price relationship. And here we can see that we have a negative correlation between them as well. So far, we have seen how you can analyze the data based on the relationship between the features and the target value. Initially, we had 13 features, out of which we selected the 4 which were more correlated with the target value. In our next lab session, we will have a look at the univariate and multivariate analysis on the dataset that we have manipulated for training our final ML model. In this lesson, we will look at the univariate and multivariate analysis of the dataset we have. Basically, univariate and multivariate represent two approaches to statistical analysis. Univariate involves the analysis of a single variable, while multivariate analysis examines 2 or more variables. Most multivariate analysis involves a dependent variable and multiple independent variables. And most univariate analysis emphasizes description, while multivariate methods emphasizes hypothesis testing and explanation. Although univariate and multivariate differ in function and complexity, the two methods of statistical analysis share similarities as well. Let's begin with analyzing the price at first. So over here, when we run this cell, it will provide us the box plot and the distribution plot for price target value. And here it is. Here we have the two graphs. This shows the price is normally distributed. There are some of the outliers as the extreme values. So to remove the outliers, we will make use of the in-quartile method known as IQR. IQR describes the middle 50% of the values when ordered from lowest to highest. So to find the in-quartile range, we first find the median or the middle value of the lower and upper half of the data. These values are quartile 1 and quartile 3. The IQR is the difference between quartile 3 and quartile 1. Here in this cell, we have the code for applying the IQR method. This will give us the outliers. Also, if you notice that we have two variables here with price UV, which is the upper value of the price, and we have the lower value of the price as well. First, we look at the outliers that are below the lower value. So let me run this cell. So here we can see we have two values, data points, identified as outliers. If you carefully observe the dataset, we see that the tax for just 5 rooms is $666, which is very high. Also, the LSTAT values are high as well. As we have seen previously, that tax and LSTAT are negatively correlated to price. This means that the higher the tax and LSTAT, lower will be the house price. Therefore, this gives some value to the two value we have here. So therefore, we will keep them in our dataset. Now I will check for the outliers above the higher value. So let's run this cell. So we have more values over here. We see that houses having price 50, the number of room ranges from 5 to 9, which is unusual. Also for these houses, tax ranges from low to high. Then for houses priced between 37 to less than 50, RM is higher than 75% of the total data points. Since RM is positively correlated to price, this can be possible reason for slightly higher house prices. Also for these houses, PT ratio and LSTAT lie in 25% to 50% of the total observation. Since PT ratio and LSTAT are negatively correlated to price, this can be a reason for a slightly higher house's price. So with these observations, we will drop the data points for houses having price equals 50, as these tend to be outliers and can be cause of possible problem toward better prediction rate. So we will keep the data points for houses having a price range between 37 to 49, as they don't have any unusual behavior among them. Now let's remove the values having price equals 50, and then we will have a look at the shape of the data before and after dropping these values. Let's run it. So now our data is of shape having 490 rows and the same 5 columns. Now let's analyze the text. Following the same procedure, we will plot the box plot and normal distribution graph for it. Alright, so here we can see that the text does not have normal distribution, despite the fact that there are no outliers in box plot for price. Instead, there are some text values that are too high. And from the scatter plot, we see that these high text values for price values range from low to high. Let's make a temporary variable with the name data frame. And here I'm storing the values in my actual data frame having text values greater than 600 and sorting it by RM value. Let's run it. So it says that we have 132 such values that meet our condition. Now let's check them. Okay, so here we have these values. Also, let's check its statistics. So what do we observe here? The RM value is the average room per dwelling lies between 3.5 to 8.78. Then we see that the PT ratio for almost all of these entries is the same and equal to 20.20. Also, the L stat for these entries lies between 2.96 to 37.97. The price for these entries lies between 5 to 29.80. All of these observations are quite unusual. It is not possible to have such high text values for all these houses. These values are most likely missing values which were imputed casually by someone. So what we conclude from these observations is that since L stat is more correlated to text as seen above in heat map, we will replace those 132 text values with a mean of remaining text values, dividing in some intervals with the help of L stat. So we will do this in 4 intervals. For interval 1, replacing extreme text values having L stat in between is between 0 to 10 with mean of other text values whose L stat is between 0 to 10. Next we have interval 2. And it's replace extreme text values having L stat is between 10 to 20 with mean of other text values whose L stat is between 10 to 20. Then for the interval 3, replacing extreme text values having L stat is between 20 to 30 with mean of other text values whose L stat is between 20 to 30. And finally for interval 4, replacing extreme text values having L stat greater than and equals to 30 with mean of other text values whose L stat is greater than and equals to 30. So here in this cell here we are doing this, and in the first 4 lines we are calculating these 4 text values, and here in line number 7 till 16 we are replacing those values with the mean ones. Let's run this cell. And it prints that values are successfully imputed. Next, let's check for the values if there exists any value that has text greater than 600. So you say we don't have any count value here. Now let's have a look at the distribution after the changes we have made. So here we have a normal distribution. In this lesson, we will continue with the remaining analysis that is left. So let's now analyze the PT ratio, that is pupil-teacher ratio, and we will follow the same method to analyze it as well. So here we see that PT ratio is not normally distributed and there are few low values in the dataset. Let's look at those values lower than 14. It can be seen that the PT ratio values for all these values are almost the same. Also, RM and price is increasing simultaneously, as RM and price are positively correlated, which is fine. And when L stat increases, price decreases, which follows negative correlation. So what we conclude is that there are no abnormalities found. So we will keep this data as it is. Now let's analyze the L stat, and I will run this cell. And here we see that the L stat is normally distributed but a bit skewed to the right. And there are some high L stat values. Let's analyze them using the IQR method as discussed previously. I will analyze the higher values that are above the upper limit. Now let's run this cell. Alright, so here we can see that we have 7 higher values, and as the L stat value for these 7 values is high, the price value is low, which follows the negative correlation and is true. Also, RM is low and tax is little higher, which means price is low, which is also true. As these observations are valid, so we don't see any abnormalities, so we will keep this data. Now finally, we will analyze the RM. Let's plot the graph. And here we can see that the RM is normally distributed. There are some low and high values for RM which we analyze, and the scatter plot for RM versus price shows a good positive linear relationship. Let's use the IQR method to check the lower values outliers. Let's run this cell. Alright, so we get the output here. We are more concerned on 2 data points at raw index 365 and 367, where price is higher while RM is very low, though RM and price are positively correlated. So now also for these 2 data points, tax and PT ratio are above 50% of data points respectively, though both are negatively correlated to median value. And for the rest of the data points, we don't see any unusual behavior. So we will delete the 2 data points with the raw index 365 and 367, as it may influence the prediction capability of our model. Also, we will keep all other data points. So let's run this cell to drop the 2 data points. Okay, so now you can see that after dropping we have 488 data points. Next, for the same analysis, we will observe the higher outlier values. Let's observe these values. So in the data points, we see 1 data point only at raw number 364, where price is very low, while RM is very high. Though RM and price are positively correlated, as we discussed earlier. Also for this data point, L stat is low and the price is also low, though both are negatively correlated. And for rest data points, there is not any unusual behavior. So we will delete this data point at raw 364, as this could be a human error while inputting the data. And we will keep all other data points in our datasets. Now let's run this cell. And now we have the updated dataset with removed value. So finally we have 487 rows. Now we are done with univariate and multivariate analysis, and now our data is ready to put into the black box, that is our model. But before doing that, we need to split our data into training set and test set And then we will make our model on the training set and test its accuracy on the test set. In this lesson, we will learn about splitting our dataset into the train and test data, which will then be used for training the model and validating it. So we have seen previously, after all the necessary data cleaning, we now have the final dataset data frame stored in the variable name Boston_df3. Let me display it for you. So this is our dataset. We have the target value as well as the features in it. So this is our dataset. We have the target values as well as the features in it as of now. And the total columns we have is 5, whereas the data points are 487. First, we will drop the output, which is the target, and save the resultant dataset columns in the variable x, as this will be the input. Then the price, which is our target value, will be the output, and let's save it in variable y. Let me display the two variables for you. And here we have the x variable. You can see we have 4 features: the RM, tax, PT ratio, and the LSTAT. Next, let's see the output y. And here we have the price target values. Let me also print the shape of x and y. Next, using the dot values method to convert it to array and then changing the data type to float 32, as SageMaker needs this data type to process the data and train the model. Now, with the help of the scikit-learn library, we will split our dataset with a test size of 30% and the random state of 4. Let's run it and then print the shape of the test and the training dataset. So finally, we have split the dataset and we have their respective shapes as well. This is how we split the dataset. In this lesson, we will train our model for the price prediction of the Boston house dataset. We have already imported the SageMaker libraries during the start of this project. So we have here the variable in line number 2, which stores the SageMaker session value, that is the access resource name basically, or you may call it as the ARN of this session in SageMaker for this project. Then we have the role, which was used while creating the notebook instance. These are the necessary parameters required as an argument for the model training instantiation. In the next cell, I am importing the linear learner library first. Then we have the bucket name and the prefix defining our complete output path where our trained model will be stored as a model artifact. Then from line 10 comes the important part, where we have defined the model parameters. So our role is the current IAM role used by the notebook running this project, which basically has the access of the S3 bucket to fetch the input data for model training. The instance type we will be using to train the model is ML M4X large. The predictor type is linear regressor. The output path is the same as defined in line number 7. SageMaker session is the current SageMaker session. We will be using 300 epochs to train the model with a total of 32 different models being trained in parallel. Loss function used is the absolute loss. And as before, to reduce the billing seconds, we have used the spot instances and maximum runtime of 300 seconds. And maximum wait time is of 600 seconds and the max wait time of 600. Let's run this cell. So we have defined the hyperparameters for the model training. Let's move on to the model training itself. So we will prepare the record set for the training and the validation set for the model. The formatted trained data is the xtrain and labels are the ytrain. These were created during the split data process. Then we have the formatted validation data record set, which has defined channel as validation and contains xtest and ytest as arguments. Let's create our training job, and once we run these cells, the training job will start and we will have our model ready to be deployed. Now I have run this cell. So now our model is deployed and the endpoint is created. Now let me show you the endpoint in the SageMaker dashboard. Here it is. Now let's start our prediction. So here we import the SageMaker predictor, and from that we have imported the CSV serializer and JSON deserializer. Reason being that the input for our model is in CSV format and the output we will get will be in the JSON format. Also declaring here the content type, the serializer, and the deserializer. We have already discussed the details of all commands that we used here in our previous project section, so I won't be discussing it in detail now and moving forward as well. Now let's start our prediction and save results in the result variable. Let's run this cell. We can see the scores for each of the X-test input in our dataset. Now let's separate the scores from the result and store them in the predictions variable. Now run this cell. And here we get the array of the scores. Let's now compare it with the actual values. So in this way, we have the comparisons of the actual price and the predicted price by our model. Alright, here is the comparison table. And we can see that the predicted values are nearly equal to the actual values. Now let's see them visually. Here I will be plotting a bar chart for the actual versus the predicted values, and you can see that both the values are nearly similar and equal. And we can see this linear relationship with the help of a scatter plot as well. So let's plot the scatter plot for the predicted values versus the actual values. Here you go. A linear graph can be seen between the two values. We can say that the model works pretty well for us, making good predictions for the price of the houses. So you can make this model more efficient by introducing some more techniques in data processing and cleaning it with some more techniques. So far the model worked well for us. So finally, don't forget to delete the endpoint as it incurred charges even if created and not used. So we will delete this endpoint. Now run this command. Okay, so our endpoint is now deleted. And here we can see that. This is it for this project on Boston house price prediction.